In all construction jobs, there will always be large quantities of odds and ends left over. The solar system is no exception. It, too, is full of this debris. On the first night of the 19th century, January 1st, 1801, an Italian astronomer, Giovanni Piazzi, was looking for something in the skies. It was a rather needle-in-a-haystack job for Piazzi, too. He didn't know exactly what he was looking for, and he had to explore a region of the sky which was about 300 million miles wide and which began about 250 million miles from the sun. Now, here is a diagram of the solar system, and we'll find out just where Piazzi was looking. Here is the sun, the controlling factor, and very close to the center of the arrangement. And here are the planets near the sun, the small planets, Mercury, Venus, the Earth, and Mars. Now, to go on out, we have to change our scale to get the rest of them in. Here's where we were at Mars. And outside of Mars is the giant planet Jupiter. And it was in this region between Mars and Jupiter that Piazzi was looking. He found something. He found a tiny planet, 480 miles in diameter, an asteroid. For that is what these miniature planets are called. Piazzi's asteroid he named Ceres, for Ceres was the ancient pagan goddess of his native island, Sicily. In the 150-odd years that have gone by since Piazzi's discovery, several thousand of these asteroids have been discovered, some of them visually, most of them photographically. For an asteroid, because of the motion of its own, will leave a faint trail on an astronomical photograph. Here is such a photograph, and in the center of it you can see a little streak. That streak is an asteroid. The camera, which was regulated to follow the stars, of course, moves past the asteroid, and the asteroid also moves and betrays itself by that tiny streak in space. Thousands of these have been discovered. About 2,000 of them have been duly elected to membership in the solar system by having their orbits verified and confirmed. But there is still a considerable waiting list of asteroids which are standing by, waiting to be officially admitted. Now, Piazzi had what he thought was a pretty good reason for looking in the part of the solar system in which he did. About 25-odd years before Piazzi was searching, there was a German astronomer, Johann Elert Bode, who, with an assist from an earlier German astronomer named Titius, had tried to lay out the plan under which the solar system operated. He did work out an arrangement which is called Bode's law, and under this arrangement of Bode's, there seems to be a gap between Mars and Jupiter in which possibly another planet ought to be. Well, there isn't another planet there. There are a great many tiny planets there. This is the asteroid belt. Now, here is Mars, and here is Jupiter, well outside of Mars, 350 million miles farther away. And in that belt, at an average distance of 250 million miles from the sun, travel these asteroids. We don't know how many of them there are. Estimates run from 30,000 to 50,000 of them, and we probably never know when the last one has been discovered. They're small. Piazzi's discovery, Ceres, is still the biggest of the lot, with a diameter of 480 miles. From that size, they range downward to good-sized mountains, a mile or two across. And there isn't very much material in the whole lot of them. We can judge that by the very small gravitational effect they have upon Mars and Jupiter, which are the closest permanent bodies to them. If we were to put all of the asteroids into one lump, that lump would have only 1,000th as much material as there is in the Earth. So you see, there is not very much there. Now, most of the asteroids travel in that belt between Mars and Jupiter. Here's a diagram that shows that. Here's the Sun again, here's the Earth, here is Mars, and here is Jupiter. And here you can see some typical asteroid paths. Here's Ceres, for example. Most of them conform. There are a few rugged individualists who go on their own and travel farther away than Jupiter and even farther, and some of them that come pretty close to the Sun and incidentally to the Earth. The closest one of these that has ever come to the Earth, the one that's come closest rather, is Hermes, a very small fellow. And here is, well, this is an artist's idea of what might happen. Hermes is here, less than a mile in diameter, and this, of course, is Manhattan Island. And small though Hermes is, believe me, it would make considerable impression upon Manhattan Island. The asteroids are the last of the members of the solar system to have a personality of their own, you might say. What we have left to talk about today is dust. Dust either clumped together or in individual grains. In the spring of 1910, the world was looking up at the sky with considerable expectancy, for Halley's Comet was due to appear. It did appear, and it was magnificent. I saw it, and I can remember it, or at least I think I can remember what it looked like. My chief memory is of a faint, tapering, greenish tail which stretched halfway across the sky, for the tail of Halley's Comet was over 50 million miles long. Halley's Comet was expected in April, and during that month, astronomers of all kinds, amateur and professional, were looking at the sky. Halley's Comet was picked up the last few days of April as a very faint object by a German amateur astronomer in his telescope. From that time into May, it grew considerably in size and in brightness as it drew near the Sun, reaching its climax about the first week in May. From that point on, it began to diminish in its appearance as it made its way around the Sun and started back to the other end of its orbit, some 2.5 billion miles at the other end of the solar system. Now here is a diagram showing the very elongated orbit of Halley's Comet. When Halley's Comet was here and had that magnificent tail, considerable consternation was felt by many people on Earth because it was known that the Earth was going to pass through the tail of Halley's Comet. And it was also known that there were some pretty harmful substances in that tail. And the general perturbation of the people was not soothed by several enterprising gentlemen who went around selling comet insurance. The Earth did pass through the tail of Halley's Comet. But our atmosphere is so tremendously more dense than the gases in the tail of Halley's Comet that it was a perfect shield, and of course, no harm whatever resulted from it. Now, notice several things about this diagram. Here is the comet coming in from the reaches of space out somewhat beyond the orbit of the planet Neptune. Notice that as it comes in, it develops this tail. Notice the direction in which the tail points. And here, incidentally, is the Earth. This is the Earth passing right through the tail of Halley's Comet. And the comet goes back to the very remote and very cold regions, some 2.5 billion miles from the Sun. Now, comets are just about 99% mystery. We don't know their origin. We don't know where they come from. One modern astronomer, John Oort, says that there is probably a great reservoir of comets somewhere in the outer reaches of the solar system, and that a comet is drawn out of this reservoir by one of the giant planets, gravitationally, of course, and started on an orbit about the Sun. When a comet is out in space, it is rather small and frozen because it's cold out there. The comet is a sphere of frozen gases. And embedded in this frozen gas are a great many tiny, stony, metallic particles, ranging from dust size up to pretty substantial objects. When a comet in its orbit comes near the Sun's radiation goes to work on this frozen sphere of gas, vaporizes. The comet grows tremendously, is distended. Comet diameters may run 30 30,000 to 50,000 miles, and even in some cases as big as the sun, almost 1,000,000 miles across. But remember, they have no more material than they did when they were tiny little spheres of frozen gas. And a comet comes near the sun. The sun's radiation, having vaporized this gas, then works on it and drives some of the gas away from the head of a comet to make a comet's tail. Some of the gas and some of these particles are blown off into space by the forces of the sun. And because the force that makes a comet's tail comes from the sun, the tail of a comet always points away from the sun. When the comet is on its way in from the outer regions of the solar system, the tail is streaming out behind it. When it has rounded the sun and is gone its way out, the tail is pushing on ahead of it. And incidentally, it is the tail of a comet that gives it its name. In the old days, before telescopes, comets, of course, weren't visible until they were close to the sun and had developed considerable tails. These tails looked to the ancients like hair streaming out, blown away. And the word comet comes from the Latin word coma, which means hair. A comet, to the peoples of the olden times, was a hairy star. Now, comets do travel in elongated orbits about the sun, but coming in at all angles, not like the other members of the solar system, almost in the one plane. Here is the central part of the solar system again. And here, in relative size and distance, is a diagram of many of the orbits of the well-known comets. And you can see how far they go. Now, what we see of a comet, the head of the comet, is called the coma. And here is a diagram of that. The very tenuous gases make the head of a comet. And there is, inside of that, a rather condensed, bright region that is called the nucleus. And it is from this comet's head that the material of the tail is blown away, as it were, by the radiation and light pressure of the sun. Comets are terrifically distant, and yet there is very little to them. Perhaps some of you in your younger days have cleaned erasers in a schoolroom and seen the sun shining through the cloud of chalk dust. Well, that's a comet. Sun shining through dust, that's what it is. Very little else. One great astronomer called comets bags full of nothing. Now, as long as a comet stays in an elliptical orbit, it will continue to make repeated journeys around the sun as long as it can stand the trip. Because this radiant action of the sun, this blowing away of gases, is a kind of an erosion, and it wears a comet down a bit. Sometimes a comet will go into an orbit whose curve is called a hyperbole, and then there's trouble. Now, an ellipse and a hyperbole are both called conic sections. They're that kind of curves. This is a cone. Now, if we make a section, a cut through that cone from side to side on a line parallel to the base, the result is a circle. And a circle is a special kind of an ellipse in itself. Now, if we make another cut, not parallel to the base, but again from side to side, completely through, the resulting circle, the resulting figure rather, the curve, is an ellipse. There is an ellipse. If again we cut the cone, this time through the base, in a line which is parallel to the opposite side, the curve that we get is a parabola. It's a little difficult to find sometimes, but there it is. There's the parabola. If we make a fourth cut, again through the base, but this time not parallel to either side, we have a hyperbola. These curves are always a little more difficult than the circles and ellipses. But there is the parabola, you see. Now, a comet drawn out of this reservoir of Oertz by the gravitational force of a planet starts out in an elliptical orbit about the sun. When a comet gets to about the Earth's distance from the sun, say 93 million miles, it is generally traveling at about 23 miles a second. As it gets closer to the sun, the sun's gravitational pull speeds up the comet tremendously. And comets have been known to travel at 300 miles a second when nearest the sun. This is dangerous, though, for that vast speed throws the comet from an elliptical orbit into a hyperbolic orbit like this. and whips it off into space in a sort of a celestial crack the whip. It's gone, lost. Now, about 12 comets come into our ken every year. Most of them are far too faint for anything but telescopes. And here is a photograph of a typical faint comet. Never could be seen without a telescope, but about a dozen of these appear each year. We have had an average of 6 big, bright, naked-eye comets every century. We had 5 so far this century. In 1910, of course, we had Halley's, and we had another one. In 1927, there was one, and in 1957, there were 2. One of them, which appeared in our northwestern sunset skies in the spring of that year, was the Aaron-Rowland comet. Another one appearing in the same part of the sky in the fall, in the northwest at sunset, was the Merkos comet. We don't know how many comets there are, really. They come and they go. There are probably about 70 of them, whose orbits take them from 3 to 9 years to travel and appear thus regularly in our skies. There are about 40 more whose orbits require a travel that takes from 9 to 1,000 years. And they, too, appear with more or less regularity. But we have seen comets destroyed by the gravitational turmoil of the sun, pulled apart. New ones are coming in, the old ones are going. We just don't know how many of them there are. Comets are usually named for the men who discovered them. Here is Donati's comet, discovered in 1858. This is a drawing necessarily because cameras weren't good enough at that time to take pictures. It must have been quite a job. Donati's comet, after it had been accepted and confirmed, was given a more prosaic designation, the year and a number. You may sometimes see a comet with a hyphenated name, such as the Aaron-Rowland comet here. That means that 2 men discovered it in collaboration, or that one of them discovered it and the other saw it first on its first predicted return. Halley's comet, of course, is the big exception to this system of naming comets. Halley didn't discover Halley's comet. That great comet has been known to return to the Earth with a few gaps in history since 240 BC. Before Halley's time, before the 17th century, comets were thought to be possibly a phenomenon of the atmosphere or some sort of emanation from the sun. Halley became interested in comets from the appearance of the great comet of 1682. And like a scientific man, he began to list and put down every known fact that he could find in history about comets. That got him into some pretty severe mathematical difficulties, which he was unable to cope with, so he went to a friend of his for help, and he couldn't have gone to a better source. For this friend that Halley consulted was Sir Isaac Newton, the Einstein of his day and one of the greatest mathematical minds the world has ever known. Now, Newton was familiar with a work that had been published about 50 years before by an Austrian astronomer, Johannes Kepler, in which Kepler formulated a series of laws which governed the motions of 2 bodies in space about each other. The motion of a planet, for example, about the sun. The motions of 2 stars in place about each other. And, of course, the motion of a comet about the sun. The result of this collaboration was that Halley was able to predict that the great comet of 1682 would return in 1758 and was a member of the solar system. Now, Halley died in 1705. The comet did come back in 1758 and was named for Halley. Probably the most magnificent memorial that any man ever had. Comets do leave a sort of a legacy for us as they pass through sky. Now, we seem to be moving, that is the Earth at least, in its journey about the sun, in a sort of a celestial dust cloud. And comets add to that dust cloud. You remember what a comet goes through when it gets close to the sun, how it's vaporized and the tiny particles in it are free and may be left loose around the sun. Well, those particles are very often scattered back along the path which the comet takes around the sun, as we see here. Here's the comet. And here, behind it, is the debris which it is scattering through the sky. Our Earth, in its journey about the sun, regularly passes through these celestial gravel pits, if you will. And they make what we call meteor showers. Now, a meteor. Well, I know all of you have seen a meteor. You can't stay out very long on any nice clear night without seeing one. It's that little bright streak that cuts across the sky among the stars, and they're commonly called shooting stars. Well, of course, they're not stars, not by billions of miles. For when you see a meteor, it is probably about 20 miles away from it. Meteor is a Greek word that means something in the air. And it is compounded of hot air and a tiny particle, this celestial dust cloud that I spoke of. These tiny particles of stony and metallic material are everywhere in space, and the Earth encounters them frequently. They plunge into the atmosphere of the Earth at speeds that range from 10 to 40 miles a second. At that speed, the friction created by the dive that the meteor takes into our atmosphere heats it up to incandescence and, more often than not, destroys it. But it also heats the air through which that meteor passes, and we see both the glow of the air and the meteor itself. Now, it only takes a meteor about as big as the end of your little finger to make a very noticeable streak in the sky. However, millions, literally, between 80 and 100 million meteors plunge into our atmosphere every 24 hours. Most of them are dust size, far too small to attract any attention. A few of them we do see as these streaks. And indeed, many astronomical photographs have a sort of a bonus in the shape of a meteor streak. The astronomer here is taking something else entirely. And a meteor plunged through the field of his camera and left this streak. This was quite a big fellow, too. Quite a sizable one. Meteors range in size, as I say, from dust size up to pretty considerable fragments, and their composition is practically 99% nickel iron. There are some with more stony material and some with a sort of a glass-like texture, which are known as tektites. The particle, the little bit of material that causes a meteor is a meteoroid. Now, if a meteoroid has enough bulk, enough mass to it, to last through, it is a meteorite. A meteorite is a meteoroid which has arrived. Now, you remember I talked about meteor showers when we were speaking of the debris that a comet left behind us. About 20 times a year, the Earth does pass through one of these old trails, and we see an unusual number of meteors. Now, don't let the word shower fool you. A meteor shower means an incidence of maybe 10 times as many as normal. Now, if you go out on a night and see one meteor in a shower, you may see 10 if you have the patience. There are a couple of notable ones which are really worth waiting up for. One is the Perseid meteor shower, which occurs on the nights of the 11th and 12th of August. It's called the Perseid shower because the meteors are posed, as it were, before the far more distant stars of the constellation of Perseus. And these stars, believe me, have nothing whatever to do with the shower. They just give it a name. Another one is in October, when we have the Orionid shower. These meteors are seen against the splendid backdrop of the winter constellation of Orion. There have been some pretty notable showers in the past. One of them occurred in November of 1833. Now, that, too, was before cameras, and we have to take the artist's word for this. This was terrific. Actual records indicate that the meteors did appear many thousands to the minute and probably frightened the poor people of that day into a state of reform. When a meteoroid, that particle, is big and robust enough to stand this plunge, it becomes, as I said, a meteorite. There are some pretty considerable meteorites. Here is the biggest one in captivity, as it were. This is the Onegito meteorite in the American Museum-Hayden Planetarium in New York. It weighs 34 tons, 85 pounds. It's about 12 feet long and about 8 feet high. It was brought back from Greenland, where it was found, by Admiral Peary about 50 years ago. Now, here's another one. Not as big as the Anegito, I'm glad to say, but this is considerable of a chunk. It weighs 24.5 pounds. Now, to put it in terms of water, 8 quarts of water would weigh as much as this little fellow does. We hope very sincerely that most of these big fellows have been swept out of space in the ages that have gone by. But there is evidence upon the Earth that the Earth has been struck repeatedly by big meteors. Fortunately, in most cases, in times gone by. There are a few modern instances. These collisions, this celestial bombardment, has left its scars on the Earth. And one of the best known and most easily accessible of these scars is the meteor crater in Arizona, near the town of Winslow. This is a pit about 1 mile in diameter and about 2,500 feet deep. No big piece of meteor has ever been found there, but a great many tons in the aggregate of smaller chunks have been picked up around the edge of this hole. This one we just saw, incidentally, is a meteor crater meteor. With all this incessant bombardment, the luck of the human race still holds, for there are no cases at all of anyone ever being killed by a meteor. And the most recent case of a person ever being struck occurred in 1954, when a woman in Silacoga, Alabama, who was dozing on her couch, was hit a glancing blow by a small meteorite whose progress was slowed by coming through the atmosphere and through the roof of her house and the ceiling of the room, and it bounced away from her. It bruised her, but the biggest trouble was who owned the meteorite. And finally, it was awarded to her, which was only fitting since she caught it. These are the minor members of the system, the asteroids, these tiny planets, comets, dust, meteors, more dust. Now, where did the whole thing begin? There have been many theories of the origin of the solar system which haven't stood up against physical laws. The most modern one is that by von Weizsäcker, who postulates a great disk of gas, dust, and debris with a diameter equal to the diameter of the present solar system, a center of the sun, which is spinning around at varying speeds. These varying speeds, according to the laws of angular momentum, decrease as we go out from the sun. Rapid here, slow here. And in between, these circles are vortices. This is the vortex theory. And like tiny ball bearings, in between these circles are the little accumulations of this dust and gas that became the planets. Now, the problem is not to find a nice, convincing way that the solar system was formed, but to find a good reason why it was formed at all.
This is National Educational Television.